Well, good evening, hams of all types and descriptions and license classes. So glad to start lesson number 4 on our series on managing and operating amateur radio repeaters. So our session for today, here's what you're going to get. We're going to cover test equipment that is needed for a comprehensive maintenance of a repeater. Up till now, we've been kind of a broad overview, some numbers, some setups, but today we're going to get deep down into the technology of testing. We're going to see the particular test setups and the protocol that's used for these tests and what your results ought to be. Next week, we'll go into responses for problems and troubleshootings. In other words, you've got a trouble at the repeater. What do you take with you and what do you look for and how do you approach the problem? The session today was probably 45 minutes. It might go a little bit long, and then we'll have an open question answer session after that. The prior videos, lessons 1, 2, and 3 are posted at my YouTube channel, which is K6KN_Bill. And the slides will be posted at our Slack site. I'm a little derelict. I haven't got the Slack site properly in operation yet, so you all will get a notification on that as time goes on. By way of introduction, as I said, I'm Bill Ragsdale, K6KN. I'm the president of the Berryessa Amateur Radio Club, and we manage the KE6YUV repeater. I was licensed as a ham at the age of 14 for a year. It was a novice license, good for 1 year, non-renewable, and I went on to other things for exactly 50 years and relicensed in 2005, and the rest is history. A quick summary on our sessions so far. The first session 1 is more like operating procedures, regulations, setup, real estate, getting the thing in operation. The session 2 went into the components of the repeater and an explanation of what they do and how they interact with one another. The lesson 3 gave an introduction to test equipment, the simplest test equipment that you can get for a few $100s and do the critical tests. This session today, the advanced repeater and measurement settings, involves some very high dollar expenses. And then finally, next week will be repeater diagnostics. And then later on, I'll have optional hands-on training where you either come to my house or we go up to the BARC repeater site and you can do hands-on with the repeater. This is our first little challenge. Last week, we asked that you would pull data sheets for service monitors, try to locate where you could buy one, roughly what the costs are, and figure out what a couple of the brands might be. We'll discuss that in our question answer session. And then also the price range is very interesting because as we see, you can go anywhere from $1,000 to $70,000 for a service monitor. Another reminder, I asked you all to be sure and get a logbook or notebook, spiral bound, college ruled. It's with the most durable, rugged notebook you can find, easy to get a hold of, because it's essential when you're working on a repeater, you log everything. When you come back 4 months later, you're going to say, what was that reading like 4 months ago and how has it changed? So you've got to have that notebook. We'll review a couple of key terms. The reflected power, when RF goes out to your antenna through cavities and feed line, a certain amount of energy is reflected unavoidably, and that's called reflected power. The standing wave ratio is a measure of that reflected power. It's a unitless reading that starts at number 1. Values up to about 1.4, 1.5 are good. Up to about 2, 3, 4 is questionable, and beyond that is bad. SYNAD. We'll see that today in great detail. This is signal and noise against distortion. We'll see how it's put together by putting a 1 kilohertz tone on top of your RF, and it's used for sensitivity measurements. Duplex generator means when you have your service generator operating, both sending and receiving at the same time. They may be on the same frequency, they may be on different frequencies, but duplex generator is a key factor when you're measuring performance. Tracking generator. In the case of a tracking generator, the generator puts out RF over a range of frequencies, and then does a display with a spectrum analyzer so you can see the response of the equipment at different frequencies. It's essential that you have a tracking generator on your service monitor. Some of the early ones in the 1980s did not, or it was an option. And DSENS. DSENS is short for desensitivity. It is the reduction of your receiver performance based on leakage RF from the transmitter. Here's the test equipment we talked about last time. We'll do a quick review. This is essential. The total cost of what we see on the screen there can be maybe $400, something in that range. The watt meter, the Bird is shown there. There are other ones that are much more economical and more up to date, but the Bird is very readily available at reasonable prices on eBay. You'll need 50 ohm dummy loads. Illustrated is both a 1 watt dummy load, the little cylinder in the middle, and then the black grid is a 50 watt dummy load, and you need both. Doubly shielded cables, we talked about that in some detail last time, but it's essential that you use the double shielded silver coax for your test equipment. The RT58 and so on has leakage, and it can throw off your measurements. You need a graphic antenna analyzer. That's at the bottom right corner there. And finally, a lot of adapters. You really can't have too many adapters. You can't have everything to everything. So very often you're stacking one adapter on another, trying to get some combination to match real life. This is the wonderful service monitor. This one is a IFR 1900. It was developed in the about 1995 onward, sold for about 25 years. It was a mainstay of the cellular phone industry. These were used very, very heavily in all of the maintenance on the cell phone industry. And when cell phone went digital, these became obsolete. And so you find them readily available on the secondhand market. They, again, we'll talk a little bit more about that. They are not economical, but they are essential. They are like the Swiss Army knife. Inside that one box, you have an RF transmitter with a very wide range, frequency range. You have a very wide RF receiver. These go from shortwave up well into microwave. The duplex transmitter is having both the transmitter and receiver operating at the same time. Spectrum analyzer shows you on the screen what's happening over a range of frequencies. Allows you to see your repeater, nearby repeaters, and look for interference and so on. And the tracking generator, as I just mentioned, allows a scan of frequencies, and you can see the signal response over those frequencies. In addition, the service monitor has many other measurements. It measures the frequency, power, and deviation, distortion, and noise levels of RF signals. It does that SYNAD measurement. It has in it 2 audio generators, and it has a digital voltmeter and an oscilloscope, and 2 or 3 more functions on top of that. It is amazing. When a service monitor today runs about $20,000 to $30,000. When they were first introduced back in the 1985 to 95, they were about $70,000. And as time has gone on, they've become electronically simpler, but they're still not an inexpensive item. And the major part of the money is because the measurements have to be absolutely precise and calibrated, and a huge amount of shielding inside the instrument to maintain that precision. On eBay, they're available from about $1,000 to $2,500. Some of the recently calibrated ones from a reseller might be $3,000. And under $1,000, they generally have some problem. They're parts only. They may have failed some kind of a self-check. Again, as I said, they must have a tracking generator. The early IFRs had it as an option. The IFR 1900 is what I have. It has a self-test built in, so you can run through that and verify before you buy it that all the internal functions are operating. It is very heavy. It is a beast to haul around. It's 50 some pounds. It has a great handle on it, and there's a carrying case for it that has a shoulder strap. It is so heavy. It's essential you have the manuals for it. I got a PDF of the manuals, and the manual is about 500 pages, but the last 200 pages are about cell phones. So I just printed off double-sided the first 300 pages. But it's essential you have those manuals because, as you can see, there are so many buttons to push on this thing. You need guidance on it. The next part of advanced equipment is the RF sampler. As you can see, there are 2 coax inputs and 1 output. This extracts a 30 dB replica of the RF signal that's passing through. These are quite wide range, and these go again from VHF into the low microwave range. You can also use it to inject RF into a input stream. It's used to measure sensitivity, noise floor, squelch, and so on. Very flexible. The pass-through can be up to 1.5 kilowatts. It's hard to believe, but that's what the datasheet says. Some of the tests that it performs is you can determine the sensitivity of a receiver, which can be down in the minus 120 dB range. We talked about dBs last time, but that is down in the picowatt range. Noise floor is the input sensitivity in real life, which allows for local RF noise in the area. So your ultimate sensitivity is degraded somewhat by real life noise to get your usable noise floor. The DSense test, we'll talk about that in some detail. There's squelch setting for your repeater. You can use it for IF centering. And the CT CSS sensitivity, it can assist in that, but each manufacturer is different, so we won't go into that. That has to be set per your particular model. And it can also does measure RF power and the modulation. There's usually an RF power input. For mine, it's 50 watts. Above 50 watts, you have to use a sampler. The return loss bridge is the last element in this little group. This goes in your transmit output between the repeater transmitter and your antennas. And this samples the reflected energy that comes back. More about that later. It's used for SWR calculation. And as a note, for the reflected energy, it picks off 10% of that goes to the detector output. And it is a low power item. You do not put this in when you're transmitting high power, you'll burn it up. It's only for passive low power use without having a powered transmitter on it. So let's talk a little bit about SYNAD. SYNAD is an ingenious method to determine receiver sensitivity. The FM modulation comes out with a 1 kilohertz, 1200 hertz tone imposed on the carrier. And at the receive end, the receiver then looks at the energy in that 1000 hertz kilohertz tone against the noise at the bottom. And when the signal is 12 dB above the noise, you are at your reference point for SYNAD. A very ingenious method and used repeatedly. As I said, this is the uniform point for many receiver tests. And 12 dB is the magic number. Here's a typical setup to make a SYNAD test. Starting at the extreme left, we see a dummy load going into the sampler. All the ports of the sampler have to be terminated at 50 ohms. The service monitor and the repeater do that automatically, so you have to put a 50 ohm termination at the input side of the bridge sampler. The output of that goes to the receiver input to the repeater, and then on the side where at the bottom there's a little red arrow pointing upward, and that's where you either take sample out or put sample in. The red paths are all RF. On the right hand side of the repeater, we see going downward to the right to the dummy load, we can see the power load. From the repeater, notice the green line. The green line is picking the audio out of the repeater, passing it back to the service monitor. So this is the measurement loop. The service monitor injects RF with that kilohertz tone, and it looks at the audio coming back and makes the SYNAD comparisons. The setup process is that you set the kilohertz tone modulated at 3 kilohertz out from the service monitor. As we said, you have the ports terminated with a 50 ohm in the input. The sampler out goes to the antenna of the repeater, and the RF monitor, the RF sample goes into the service monitor. Here's stepwise how we apply that SYNAD method. First you remove the CT CSS tone requirement at the repeater, and you set the RF generator to a low value, somewhere around -90 dBm. Set the squelch fully open so that you hear the tone coming through. And now you increase the RF level until the SYNAD version value hits 12 dB. If it goes higher than 12 dB, you back off and you hum up and down until you get a nice 12 dB level. And then that becomes your reference point for the following tests. So as I showed a moment ago, this is your setup going into SYNAD. The technique is, or the method, the purpose is to measure that raw minimum receiver sensitivity with nothing else in the way. What is the signal level that the repeater will respond to? So in this case, as we had before, there's a 50 ohm load as a sampler input. There is no antenna connected. We reduce the squelch, and now at this point, we increase the service monitor until we get the 12 dB SYNAD readings. So that is the first reading that appears on the service monitor. And remember, the sampler drops 30 dB. So if you're at -90, the real value the repeater sees is -120. So once you reach that SYNAD 12 dB point, you just record that repeater sensitivity. And here's an example taken off of a service monitor. The upper yellow circle shows -125 dBm. That is the sensitivity value, and the SYNAD at the bottom is 12.2 dB. Now notice I did this one without the sampler. So the -125 dBm is the actual energy that is delivered to the repeater input. To do a noise floor test, we now add in the antennas and the feed line and the filters on the input side. Now we're in real life because we have the environment, the RF environment being added into the input of the receiver. So in this case, the sampler now is fed by the cavity filter's feed line antenna, and we repeat the SYNAD test exactly as before. In this case, we'll expect that the RF level is a few dB above the prior sensitivity, say -118 dB. That difference is due to local RF noise. It could be power line noise, it could be atmospheric noise, it could be other RF sources in the area. If the differential is more than 4, 5, 6 dB, you should investigate to verify what are the noise sources and is there anything you can do about it. In our example here, the noise floor comes out at -85 dBm, and this was done with the sampler. So the -85 -30 dB is -115. So this is -115 dB level. That's 10 dB more signal required than before, which shows it's a fairly noisy RF environment. Descends. This is the setup for descends. In this case, the dummy load on the right-hand side has been replaced by the full setup at the repeater, the filters, the antennas, and the feed lines. Other than that, it's a SYNAD test. The dreaded SYNAD descends. Dreaded meaning that if you have descends, sometimes you'll get complaints from knowledgeable users. What it means is when someone comes in with a low signal level, they can unkey the repeater. The repeater will kick on for a moment and then it will shut off because the increase in RF level has actually hit the squelch threshold, and the thing sometimes will chatter. Sometimes you don't get operation. Sometimes someone with a good signal will the signal be reduced slightly when they begin to talk, and the noise level will go up. So descends bad. And it is due to transmitter RF feeding back and getting to the receiver input and desensitizing the receiver. So in this case, we have our full setup with all of our antennas connected. We key the transmitter while repeating the noise floor test. So we set up the noise floor test, we see that dB level, key the transmitter, and then if the SYNAD 12 dB level changes, readjust, and that increasing signal level above the noise floor is your signal you have descends. And in a modern contemporary repeater, you should not have any descends. Some people think it's the antennas. It is not. It is most often by inadequate feed line shielding. It means you've got RF in your shelter area coupling from input to output. It may be that the filter cavities are not appropriate. They're not within spec, not enough elements. There's a small chance it could be connectors and a small chance it could be intermodulation. If you have incompatible metal surfaces in the immediate area, sometimes they can generate RF harmonics just from the RF that's in the area. Squelch shedding. Again, everything's in place. All your antennas, equipment, feed line is in place. You deactivate the CT CSS tone. Again, set the generator down to a low value, minus 90 dBm or so. Set the squelch wide open so you can hear the tone being heard. And you increase the RF level until the SYNAD reaches 12 dB. That's exactly what you would expect. Now you increase your squelch setting on the repeater, following the instruction books for that particular model, until your audio silences, your squelch closes. Then you simply decrease it a very slight amount until the squelch reappears. So the idea is that with a SYNAD below 12 dB, your repeater should be muted, and as the signal level gets up to that 12 dB level, it will unmute. Next measurement we're going to make is transmitter frequency. As I said earlier, that the service monitor will accept 50 watts of input on a continuous basis. However, our repeater puts out 60 watts. So in that case, we put a sampler in line, and so we're pulling off a replica of the RF, but with a 30 dB attenuation. And this is what we see. Top right is the frequency, and from the setting, we were set at 146.37, and instead the actual frequency is 146.36991, or an 85 hertz deviation, which is totally negligible. A few hundred hertz, you might do something about it, but this is totally negligible. In this case, the service monitor is simply receiving, and you put in a copy of your service monitor output. Make the test. Most repeaters have some kind of a frequency trim. They're digitally set these days and have internal frequency reference, but they usually have a way where you can put a small shift up or down from that internal reference to bring it right on frequency. There are several ways to measure the output power of your repeater. The first way is to a watt meter, by far the quickest and the best way. Watt meter you can do in 1 minute. Service monitor takes you 3 to 5 minutes to set it up. Into a service monitor, you can connect the repeater directly, observing that 50-watt limit. Or if you go over that limit, then you use the 3 dB, 30 dB sampler. Here's the simple connections with the transmitter. I would generally do this into a dummy load. There is no sense putting out RF on through your antennas if you don't have to. So at the bottom left, we see the forward power level is just a little bit over 60 watts, and the reverse power level is 2 watts. With the Bird meter, there is a little dial on the front. You flip the dial 180 degrees and you get the reverse power. This is how we use that information. We're going to compute our standing wave ratio, which is normally the number that we all work around. So we see we have 60 watts forward, 2 watts backwards. Dividing the 2 by 60 and multiplying by 100, we get the percentage of power being reflected. In this case, it's 3.3%. Look down at that table, and you can see the reflected power percent. And there's a value at 2.78, which is about 4. We're a little bit above that at 3.3. And the next step up is SWR of 1.5, and we're a good notch below that, so we're 1.4. This is okay. In real life, it's okay. Even up to about 1.7, I think, is okay. It's nice to be 2, 3, 4 if you possibly can. This is the way you measure the transmitter power output into the service monitor. Again, the bridge is in there extracting the power. Now let's talk a little more about the return loss. Earlier, just a moment ago, we saw it done with the watt meter. We can make the same measurement with the service monitor, but this setup is a little bit more complicated. In this case, on the transmit side, the service monitor is outputting on our repeater transmit frequency, which goes to the input side of that coupler, and the output side of the coupler goes right back into the antenna input of the service monitor. So the service monitor is monitoring the output circuitry through that sampler. The output goes to your filter cavities and your antenna. So there is some amount of power reflected back from the antennas, back through the cavities, back through that return loss bridge, and it appears input to the service monitor. And then we analyze that. The method we follow is that after we get the value, we use that tracking generator to set up the return loss bridge, as I mentioned. We replace the feed line cavities antenna with the 50 ohm resistor. So in this case, we are going directly. Yes, I'll think of my own thing. Oh, that's right. The feed lines are in place. The feed line cavities antenna are in place. I'll take that back. Start over. First, we need a baseline reference. So the cavities are taken away and the 50 ohm resistor is used. And so now we're measuring into essentially a perfect load. There should be 0 reflected energy, and that is our baseline. Now we replace that dummy load with the feed line cavities antenna, and now we measure the dBm signal again. And the difference is the reverse attenuation in dB. 20 dB or larger attenuation is good, and that implies an SWR of 1.2 to 1. We calculate this by a chart. There are ways to do it, paper and pencil, but you don't want to do it. You want to find a chart. Here's an example now of the reflected energy. Notice that the reflected energy is the minimum at our transmit frequency. This is because the cavities and all of the output feed lines are tuned to accept energy in that level, and therefore the minimum energy is reflected. So on the chart at the right, we see that a 20 dB of return loss implies an SWR of 1.2, which is good. About 30 is about as good as you can do, 30 to 40. And the return loss bridge itself generally has the 30 dB return loss down in the like 1.03 area. Another way to do the SWR tests we discussed at the last session, and that is by using an antenna analyzer. By far, this is the easiest way. The return loss method might be good in some industrial situations, but by far and away, a handheld graphic antenna analyzer is the way to go. You simply connect it on a passive basis out through your cavities to your antenna, and then you get a plot such as you see on the upper right, and at the bottom will be the SWR. In this case, that one is 3.67, which is not at all good, but I don't even know what it's from. Now we're going to talk about transmitted deviation. We use a deviation in ham radio of 5 kilohertz, and it is essential that we keep we set our deviation not to exceed that, but we do want to have use the full bandwidth if possible. So in this case, we have the repeater transmit side go through a sampler again to a dummy load, and then a portion of that feeds back into the analyzer for analysis on the receive side. On the transmit side, notice on the left-hand side of the service monitor, we have a transmit output, and we'll discuss this in just a moment. So the transmit output on the left side goes into the repeater, and the repeater's output circles back down to the bottom. So in this case, the service monitor is in duplex mode, sending and receiving at the same time on the same frequency. We set it up so that the RF is at say 50 dB with a kilohertz tone with a 3 kilohertz deviation. And since we have a 30 dB sampler in there, the repeater is seeing minus 80 dB. And minus 80 dB is just a good representative operating day-to-day signal level. The service monitor input is that sampled RF analysis. And now we simply adjust the repeater deviation. You look in the manual for your repeater and see how to adjust that. But you adjust that up or down until your service monitor says your transmit deviation is 3 kilohertz. You know you set 3 kilohertz on its input. That gets translated to audio. It goes into the repeater, and it comes out again at a 3 kilohertz deviation. This is a quick exhibition on cavity tuning. The service monitor gives you a beautiful graphic picture of the response characteristics over a range of frequencies. As a little aside, it is very unlikely, highly unlikely, you will ever make field adjustments of cavity filters. They're normally factory set precisely and perfectly, and the only reason you would ever change them is if you repurpose them into a different location somewhere else. But there is no need to retune cavity filters. I can think of no time during troubleshooting or analysis you would ever want to change them. The cavities are tuned individually. You can tune them to their individual center frequencies, and then you verify the operation in their series connection. There is a little bit of interaction between them. It's a little bit of a experience art getting to turn the cranks on them. They all have a knob on them, sometimes a wrench. There are a couple of sensitivity or bandwidth settings, and there's the interaction between those. We check them by putting the service monitor into a duplex configuration. So the output of the service monitor goes through the cavity and right back around to the input, in which it's displayed on screen. And we set the generator centered on the desired cavity frequency. For a pass filter, we adjust the cavity settings with a trade-off observed between loss and bandwidth. That is, if you tighten the bandwidth on them, the loss goes up, and if you loosen the bandwidth, the loss goes down. And so you have to make the judgment call how much loss can you stand from all the cavities in line versus your selectivity. And the typical loss range of the full set is somewhere probably close to 1.5 dB. Single cavity might be a half a dB, but if you're up in the 3 dB, remember you're losing half of your energy. 3 dB is losing half your energy. 1.5 dB is you're losing about 20% of your energy in the cavities. A notch filter is the same, but a mirror image. Instead of having a peak, they have a minimum. So you turn the knob on the filter back and forth, adjusting for the lowest, most negative dBm value. And here is a picture of tuning a pass cavity. It's set in this case to 146 megahertz. And then I've set some markers on the left and right. On the next slide, we see, on that slide, we see those markers. And the markers in this case are placed 3 dB down. So you can get a relative indication of the bandwidth. This is fairly spread out. Normally you would have the image compressed a little bit narrower so that the side skirts would be coming down. But notice the attenuation. The peak is about minus 42 dB and the skirt on the outside edge is 60 dB. So from the peak to that skirt edge is about 18 dB. 3 in a series would go 18, 18, 18. So that is about 60 dB, which is not an unrealistic number for a series of cavity filters in line. Maybe it's a little bit high, but 60 dB in sequence is a good number. This topic we'll just jump right over. It is desirable to have your input receive signal going through your IF bandpass. As we know with super heterodyne theory, the repeater input is translated and goes through 2 IF stages. It is in older tube units and transistor units, they were adjusted by a screwdriver and they could have drift. In the modern repeaters, it is unlikely you're going to have any problem on your IF centering. But I put it in here just for completeness. 10th method is to use the SYNAD setup for SYNAD 12. And now you increase the RF power by 6 dB. So whatever it was at the base test, you increase the power by 6 dB, which means you're actually subtracting 6 dB. In other words, it's making the number larger. You then adjust the transmitter frequency up and down to find the new 12 dB SYNAD points. Essentially what you're doing is you're examining the skirt side down 6 dB on each side using the SYNAD test. You find those two frequencies at the new 12 dB points, average them together, divide by 2, and that is the IF passband center frequency, which you hope is the same as your receive frequency. Sometimes there would be a way to trim to center that up. I know on our older repeater we had, it was a transistor, we had to do this realignment once, but it should not be necessary to do it on any contemporary repeater. The mathematics on it is we see graphically, we take the upper and lower 6 dB points, add them together, divide by 2, and that gives us the center of our IF, at which point it is symmetrical in its pass-through. This is compared to our desired frequency, which is 1.4, that slide has an error, it should be 146,970. And we see the net result is that we're 200 hertz off in our pass band, which is quite acceptable. So our next lesson, what can go wrong? We're going to look at common failures and what kind of equipment would you use and how would you approach that situation. We'll propose some simple diagnostic tests, and then if things get sticky, you have to do some engineering work where you bring the service monitor in. And we'll show you a couple of methods for systematic troubleshooting. So your assignment for next time is to put your thinking hat on and make a list of 3 or 4 some items that could go wrong in a repeater. So what do you think could be the list of problems, and then the approach the equipment and the testing that you might do to solve that. And we'll go through a number of these. So for references, one of these days you're going to receive the invitation to Slack, and they will have our all of our material posted on it. It's in preparation currently. The YouTube channel, K6KN Bill, has 3 programs on it, and we'll shortly have this 4th one. Repeater-builder.com is a gold mine archive of wisdom accumulated over the years from repeater builders. And then the ARRL Handbook for Radio Communications, every amateur should have, and also the ARRL Antenna Book, every amateur should have. So we'll now stop the recorder, and we will go into our discussion period.